known for. The broad beams we can talk about later if you want to, but let's just focus on the microbeams. So what does it take to make a microbeam? Well, biologist comes to me and says, I want to irradiate these cells, and I want to irradiate every single one of them, and I want to know that they all got one alpha particle through their nucleus. So, well, you need a source of particles. We have an accelerator. You need to be able to detect the particles and say, yes, you've got dose in your sample. You need a way to turn it off so that you only get dose where you want it. You need a way to focus it. You need to be able to get it down to that single cell so you know where you're shooting. You need to shoot straight. The issue is, it doesn't matter how well you can shoot straight if you can't see what you're shooting. So you need to have imaging as well as the physics of the focusing of particles. And then you need a way to move from one cell to the next. And it's all controlled by computer. This scale, everything needs to be controlled by computer. We're at the scale of about 1/10 of a human hair or smaller. So we look at this. Here's a quick walkthrough of the layout of our microbeam system. We start with our particle accelerator. We then have some beam defining slits. This tells us, this is our initial definition of what size our beam is and where is it. We have a little bit of steering and then a big magnet to bend it, to get it vertical, so we can bring it up through the bottom of the dish. Again, another set of apertures, again, to tell us where the beam is, so we know exactly where we're at. We then have a focusing element, this electrostatic quadrupole triplet, and I'll talk about that in a couple slides here. We have a second quadrupole. One lens focuses, creates a spot for the second one, which cleans it up. And then the beam comes out of our silicon nitride window here. That's 500 nanometers thick silicon nitride holding back all of our vacuum system. But it doesn't scatter the beam, so we can actually have the focus for the beam outside of the vacuum system. This little window is about a millimeter across. And you'll see this little ring. We got a ring here on top of our stage where we can put our cell dish. We plate our cells right here in the center, and then we can actually move it around and irradiate the cells right there. On the end station, the cell dish goes right here, the beam comes up. We have our fine positioning stage moving from cell to cell. But we also have to do the imaging. So we have a microscope and the associated camera system. So we have the focus of our beam and the focus of the microscope have to come together at the same point. You need to be able to shoot straight and you need to be able to see your targets at the same time. So here's another in-station. If you remember, I said that we use an electrostatic quadrupole system. This is actually a permanent magnet system. So we actually use permanent magnets to focus it. So we have, this is a general microbeam system. You have a system where you have a source, object aperture, focusing elements. Again, beam preparation. And then the focusing magnets. This is a little bit more photogenic. You can actually see the aperture, the focusing magnets, all the little knobs and stuff that go to that. The nice thing about this system is when we renovated the third floor, we took this system apart, put it in boxes, came right back, put it together, and within 2 hours we were back to where we were. It's permanent magnets. As long as you don't move the knobs, they stay there, everything works. It's a wonderful little system. But you also notice that it's on 2 floors. The object aperture is down here at the bottom of our right about our second floor, and the end station is up on the 3rd floor. It's about 3.5 meters from the object aperture to the top point. I talked about quadrupole focusing. How does this work? This is actually how we focus the beam. For magnetic, think of north-south, north-south, but for electrostatic, think of plus-minus, plus-minus. As a charged particle moves through either a magnetic field or electric field, it'll get deflected by that field. And so you'll see we have field lines here, and what happens is in a magnetic field, it pinches in one direction and stretches in the other. For an electrostatic case, it pinches in one direction and stretches in the other, but it's tilted at 45 degrees in the magnetic case. But the interesting thing is that the squeeze is stronger than the stretch. So if you stack a bunch of these together, you can squeeze in this direction and squeeze this way and squeeze and squeeze, and you come out with a really small spot at the top. So we've designed systems. This is an electrostatic triplet again. So it's electrostatic, so it would be plus, minus, and then minus, plus, and plus, minus, again, stacking at 90 degrees, squeeze from the different directions. We've actually gone to a double system where we have two lenses actually working together. And the first lens does a good job focusing, and then the workhorse is the second lens. What can this do for us? Well, the first microbeam we had in 1996 was just a hole punched in a piece of steel. So you shine your beam at it, what comes through is what you get. That we got down to about 10 microns, small holes. But the problem was, anything that hit the edge of the hole scattered off. You couldn't guarantee that you were just getting dose there. So we went to these electrostatic focusing systems. First one was a quadrupole quadruplet. It had 4 elements. We got to about 5 microns. Found out that the triplets work better. The elements are a little bit longer, and we actually got down to 1.3 microns. And our double system that I just showed the model for, we get down to half a micron. So, how big is that? It's hard to imagine sometimes. If you think of the average human hair is about 50 microns. This is 100 times smaller than your hair. That's how small we get. But that's the scale of things that we want to be shooting at. And some of the things we want to shoot at are smaller yet. That's where our future is. Well, as I mentioned, great, we can shoot straight, we can shoot really small, we're really good at that, but we need to be able to see what we want to shoot at. So we actually have a microscope system here, and this is a